morning, one and all. Myself, Dr. Vilas Kanthade, School of Mechanical Engineering. Today, we are seeing the first experiment of our subject of dynamics of machinery. Now, our first experiment's name is to determine the natural frequency of single degree of freedom system of damped free vibration and to determine or to calculate its damping coefficient. Now in this experiment, so this is the aim. Now in this experiment consists of some elements of the vibratory body or the vibratory system. Now before going into the details of this experiment, just I would like to explain you the some terminology or some terms which are related with this experiment. So first term it is that is that there are two types of, so basically there are two types of vibration, that is the free vibration and forced vibration. Now free vibration, whenever any body, so whenever any body, suppose see here, now this is the body, just I am rotating it, means I am applying one time external force on this body and removing this force. Now whatever may be this body is vibrating, so this kind of vibration or this kind of oscillations of this body is called as the free vibration, Now suppose the same system is here and I am applying continuously twisting moment on this body like this one for each oscillations. Then whatever may be the vibration or oscillations occur, so this kind of oscillations or this motion is called as the forced vibration. Now whatever may be the frequency of this free vibration is called as the natural frequency, and whatever may be the frequency of forced vibration is called as the forced frequency. Now again there are another two types of vibration, that is undamped free vibration, the undamped vibration and damped vibration. Now what do you mean by the undamped and damped vibration? Now undamped vibration means damped, so we are providing any external resistance against the motion of the body, against the motion of the body. So this resistance is called as a damper or damping. And now undamped means if there is no any external resistance is provided against the motion of the vibratory body or the system is called as the undamped vibration. Now these are the four important terms. I think so far you might have studied in your theory lecture also. Now also one more term is related with this. Now when we are talking about the damped vibrations, then therefore definitely, so we need to find out, because this damping vibration which depends upon the damper. Now damper means how much its size, what is the shape of the damper, and whatever may be the oil or whatever may be the fluid which are used in this damper. Now depending upon the fluid, which type of fluid is used in the damper, depends upon that its viscosity, then it will resist or it will provide the resistance against the motion of the body by that certain amount. Now that certain amount which is totally depends upon the viscosity of the respective fluid. Which kind of fluid you are using in this damper, that is very, very important. Now in our experiment, now when we are in our experiment, now again we are using here right now only the water instead of oil, or we can use the water as well as oil. But today we are using only the two kinds of the medium or the fluid, that is one is the air medium and the another one is the fluid, that is the water medium. Okay. Now again before going into the details of these experiments or before performing the experiments, just I would like to again explain you, so what do you mean by the damping coefficient? Now damping coefficient, it is the ratio of the damping force or the resistance force per unit of relative velocity between the two elements or between the two parts. Okay, this is the damping coefficient. Now one more important parameter is required, that is the damping factor. Now the damping factor, it is the ratio of damping coefficient to the critical damping coefficient. It is the ratio of damping coefficient to the critical damping coefficient. Now the question arises, what do you mean by the critical damping coefficient? Critical damping coefficient, it is the value of a damping coefficient at which the frequency of damped vibration is 0 and the motion becomes the aperiodic. Now if we took the ratio of these two coefficients, that is the damping coefficient and critical damping coefficient, so that is the damping factor. So this damping factor plays a significant role so to provide or to stop any vibratory motion or to make it stationary. So it depends upon. Now again, so there are, depending upon this damping factor, there are again three more types of the damping system. That is, the first one is the over damped system, critical damped system, and under damped system. Now I am not explaining all these types of the damping system. You will see all these type of damping system in the theory part. But we require, so now in our case, this is the under damped system, not the over damped or critical damped. This is the under damped. Now over damped system is when the damping factor, it is denoted by a symbol, that is zeta, and this, if this zeta value or the damping factor value, if it is greater than 1, that is called as the over damped system. If the damping factor is equal to 1, that is called as the critical damping system, and if the damping factor value is less than 1, then it is called as the under damped system. Okay, now all these terms are related with our experiment. There is again one more term is required in our experiment, that is the logarithmic decrement. So this logarithmic decrement, which is also called as the rate of decay of the motion, rate of decay of motion. Now what do you mean by this logarithmic decrement? Logarithmic decrement, it is the again the ratio of the it is the logarithmic ratio of two successive amplitudes. Two successive amplitude is called as the logarithmic decrement. It means that it is mathematically 1 upon capital N into log in bracket x1 upon xn plus 1, where capital N is the number of oscillations and small n is equal to 1, 2, 3, 4, 5. That is the number of oscillations. Okay, capital, that is small n, 1, 2, 3, 4, and capital N is the total number of oscillations. Okay, now how this experiment? Now it is, see, this is now the one shaft whose one end is fixed at this beam. Okay, it's at its another end. This rotor is attached. Okay, having its diameter is 260 millimeter, and the diameter of this shaft is 3.5 mm. Now again, so to this rotor and to this shaft, the one drum is attached. Now in this drum, we are inserting or we are filling the liquid, any kind of liquid or any kind of the fluid. Okay, now right now we are using here the water. Okay, now how this experiment is to be performed? Now initially, because we are seeing the torsional vibration, therefore we are applying the twisting moment on this complete drum by some certain amount. Means we are twisting this complete drum by some certain angle, and then this twisting moment force is, or this twisting torque will be released like this one, and then we are counting it's the number of oscillations. Now from 5 to 10, or say 5 only number of, and for this number of oscillations must 1, 2, 3, 4, 5, like this one. We are measuring the number of oscillations, and for this number of oscillations, again at the same time we are noting down it's a time, how much time is required for this total number of oscillations. Okay. Now we are giving the twisting moment to this drum. Okay. Now we are again calculating the how much time is required for the number of oscillations. Now we are considering here number of oscillations are 5. So therefore, now our assistant, department's assistant will help me for counting this number of oscillations as well as the time. Yes, that is power. Okay. Now see, I am twisting. I am applying the twisting moment on this drum, and just I am releasing because it is the free torsional vibration. It is free. Therefore, I am applying one time twisting moment and then releasing this twisting. 1, 2, 3, 4, 5, 6. Now we have taken the number of oscillations 6, and we have measured the time for required that 6 number of oscillations. Now here we are performing 2 experiments. Now without applying or without filling the fluid and before. Now here there is no fluid is inside this drum. Okay, you can show here. So there is no fluid here. Now it means that we are performing this experiment in the air. Means first of all we are seeing when the air as a resistance. So air as a resistance and water as a resistance. Okay, and now we will count it's the number of oscillations as well as the time required in the air media itself. Okay, now just I am applying again one time. See how this experiment is performed. Now we are measuring its oscillations. In this way, so we got the amplitudes of this torsional vibration, that is the torsional in the ear. Okay. Now we are marking the center line or the center line from this amplitude, and then we are measuring the amplitude of the first this amplitude of this first oscillations, and then n number of units, that is the sixth amplitude, sixth oscillations amplitude. Okay. Now we are drawing one center line from this curve or from of this graph. Okay, and then we are measuring this value, that is x1. This is called as the amplitude. Okay, and then we are measuring the sixth one, 1, 2, 3, 4, 5, and 6 oscillations. Okay, that is n plus 1. Yes, first one. Then we are measuring again, that is the its amplitude, and then we are, if we took the ratio of these two amplitudes, then that is called as the logarithmic decrement. With the help of logarithmic decrement, then we are calculating it's the natural frequency, that is the damped natural frequency of this torsional vibration. See, we have filled the water here, because firstly we have performed the experiment with the help of air only, without filling the water. Okay. Now right now we have filled the water, so till this disc should be immersed in the water. Okay. You can see here right now. So this is the water. Yes. Okay. Now again, so we will do the similar way the experiment. So first of all we will count the time which is required for the number of oscillations. Here again we are considering the sixth number of oscillations. Let us, we will see. So I am again applying the one time force. Now this is the damped vibration. Now this is not the this is not the undamped, because in the previous case there is no any water or there is no any fluid. Okay. Now here it is called as the damped, because the damper, this water will act as a damper, damper, because which is having some viscosity. Therefore, now see here. Now, so I am rotating. Yes, 1, 2, 3, 4, 5, 6. Then see here again. Now we will again do the similar way. So it's again amplitude. We will measure amplitude. Now see, just again we will perform. So I am again one time again twisting moment, and then counting its a time. With the help of this mechanism, again we are recording the its time also similarly. See that in the previous graph and this graph it is totally different. Yes, you can again see here there is a large amplitude, and after some certain time this amplitude goes out decreasing. Why this is happened? Because it's due to the viscosity of this water, and that's why this the motion of this body will be a stop, or these oscillations will be die out after some certain time due to this damper. Now this is the now again we are measuring this amplitude from its center line up to this first oscillation, our first cycle, and after the last cycle, that is after the sixth. Okay, again we are measuring its amplitude, that is xn plus 1, and then taking its ratio, and after performing this and then calculating its all the parameters, then we will verify whether the theoretical natural frequency and the this experimental frequency, whether both are same or not. Yes, so this is our ultimate aim, to determine the again a damping coefficient as well as the natural frequency of this damped torsional vibration of this single degree of freedom system. Thank you.
So as we know, so just we have seen the experimentation work. So we have seen it's a theory part. Now we will do it's a calculation, how it is to be calculated. Now, so first of all, this is our observation table. In this observation table, so the first column, it is the medium. Which medium we are going to use? That is, we have used two medium that already we have seen in the experimental work. That is the air and the water. Then the second column, it is the number of oscillations, that N. So for the air damping, whatever we have twisted the drum, and we have measured the number of oscillations. Suppose say the number of oscillations may be measured from 5 to 20. So you can take any one. So just suppose say 5. So number of oscillations are 5 in the air. Then its average time is to be calculated or is measured. So for this 5 number of oscillations, suppose if it comes around about suppose 9 seconds, it is in 9 seconds. Okay. Now the first amplitude. So now as we know, so also we have seen one graph on that paper. So in the experimental work, so that graph is coming like this one. So this graph is like this one. Yes. Now this is the graph we have got, or this is the amplitude or the vibration we have got. So by rotating that drum in the air. Okay. So without using the fluid medium. Now if we have drawn the center line passing through this oscillations or through this sinusoidal wave. Now first of all we have to measure this one. So this distance. So this is called as the first amplitude of the first oscillation, and it is always denoted by that is x1. This is measured in terms of, so that is in centimeter. Now suppose we have considered here the 5 number of oscillations. Therefore we will measure 5 oscillations. This is 1 because from one side 1, 2, 3, 4 and 5. This is the fifth one. This is the fifth one. Okay. Therefore now this is your, we can call it is the n plus 1. N plus 1 oscillation. Now suppose this value is coming, suppose that is again so 4.8 if I am saying, and suppose n plus 1 amplitude is often suppose 2.1 something like this one. Now so we got the number of oscillations 5, that is the average time 9 seconds, and 4.8 and 2.1 in this way. Now let us we will do it's a calculation how it is to be calculated, because our aim is to determine the natural frequency, that is the natural damped frequency of the single degree of freedom system for the torsional vibration, and also to determine its a damping coefficient. So this is our objective, or this is our aim. Now how to determine it? So see, it's a calculation parts for the air. Now we are calculating, or we are doing the calculation for air differently and for water lateral. Okay, so first of all we will do the procedure for the air. Okay. Now so we need, already we have seen that. So what do you mean by the logarithmic decrement? Logarithmic decrement, it is nothing but it is the ratio of the two successive amplitude. Okay. Now it can be denoted by, that is see mathematically, delta E is equal to 1 upon capital N in multiplied by logarithmic multiplied by again x1 upon xn plus 1. Now x1 already we have got from that table. So from the graph, that is already we have calculated from first, that is x1 value, suppose say 4.8, and xn plus 1 is nothing but it is a 2.1. Now if you do the calculation for this delta, so from this calculation we got the delta, say suppose the equation number 1. Now second, we need to find out the another parameter, that is the damping factor. It is mathematically it is denoted by zeta. Okay, and it mathematically it is expressed by, so zeta is equal to delta upon under root 4 pi square plus delta square. Now the question may arise in your mind, sir, how it comes? Now it is same. We can see this part in the theory portion. Okay, but just keep in mind. So how the zeta or damping factor is to be calculated? As already we have seen, what do you mean by this damping factor? Damping factor is nothing but it is the ratio of damping coefficient to the critical damping coefficient. And now in order to determine the damping coefficient, that's why we need to find out first of all the damping factor from the logarithmic delta. That's why initially we had calculated the logarithmic decrement. After that we are determining the damping factor, and therefore now from this equation we got the damping factor. Okay. Now but again we know the zeta is equal to C upon Cc. So C is nothing but it is the damping coefficient, and Cc is nothing but it is a critical damping coefficient. Now from this equation, so we can do it's a cross multiplication. Therefore C is equal to zeta into Cc. Now there the critical damping coefficient, this Cc value is given to you. Okay, in your experiment one. Now, so you can substitute this Cc value multiplied by this zeta from this equation number 2, and you will get the damping coefficient. Yes. So that is our first aim is completed, that is to find the damping coefficient. So from this equation number 3. Now we need to find out again further that is the damped frequency. Now how it is to be determined? So damped frequency is denoted by Fd letter. Therefore Fd means D means damped, F means air frequency. Therefore Fd is equal to damped frequency is equal to natural frequency multiplied by under root 1 minus zeta square. Where? But this natural frequency is again unknown to us. Therefore this natural frequency will be calculated by the relation is equal to under root Kt upon Ip. So Kt, it is the torsional stiffness of the shaft, and this is the polar moment of inertia of the shaft. Okay, so from this equation, now the again question is, sir, how we should get this torsional stiffness of the shaft as well as this polar moment of inertia? So again these values are given to you in your set, in your writer. Okay, therefore from this equation, if you substitute the value of Fn zeta value from this equation number 2, and therefore you can get, so this Fd, so this value whatever may be the obtainer, it is nothing but it is the theoretical value of damped frequency. Now again we have to compare the theoretical frequency with the experimental damped frequency. Now here we have got the theoretically this value, that is analytically. Okay, now we will compare this value with respect to the experimental value. Now how it is to be determined? So as from this observation table, so we know, so that is time period. So the average time is known to us, that is suppose 9 seconds. Total number of oscillations are 5. You can substitute the value of that is 9 upon 5 like this one. And also we know the frequency is equal to what, it is the reciprocal of time period. Therefore, if you substitute this value in this equation, you will get this damped frequency. Okay, so this is the experimental value. Why it is called an experimental value? Because we have taken this data from the experiment work, from the experiment. This 5, 9 and all these things. And therefore, now if you substitute it here and calculate it, then and compare, so this equation number 4 and 5. And then I will write down conclude whether both are same or not. It is mostly observed, so both are is coming near to each other. Okay. Now similarly, you can perform the this calculation for the water medium also. Okay, the procedure will remain the same. Okay, as well as the observation table will also remain the same. So I think so far you will get this idea. Okay, thank you.